Yes. You can do this, you know.
Sure. So it's easy.
In the meantime, let me briefly introduce our next speaker. So our next speaker is Mohamed Wahib. He is a team leader of the High Performance Artificial Intelligence Systems Research Team at RIKEN Center for Computational Science, Kobe, Japan. Prior to that, he worked as senior scientist at AIST Tokyo Tech Open Innovation Laboratory, Tokyo, Japan. He received his PhD in computer science in 2012 from Hokkaido University, Japan. His research interests revolve around the central topic of high-performance programming systems in the context of HPC and AI. He's actively working on several projects, including high-level framework for programming traditional scientific applications, as well as high-performance AI.
Thank you very much. I guess I should start right away. Okay. Thank you for the introduction. I'm here presenting this work on behalf of Linqi Zhang, who was the first author in this work but couldn't make it. This will be speaking about exploiting Scratchpad memory for deep temporal blocking on GPUs. I'll jump right away. As you can see from the top figure, as we are moving from bytes to flops, if you look at the x-axis on the top figure, and those are data center grade GPUs starting all the way from Kepler to what's announced by Hopper, you can see that the bytes per flop are dropping. This is, of course, not a new finding. It's what people call the memory wall, and has been existing for, since the 90s on CPUs, so it's not unexpected to see it on GPUs. However, if you look also, well, it's the same for consumer grade GPUs, so I guess it's not a big difference here. So what that leads to is obviously the case that a lot of the codes will be memory bound, meaning that you would run into cases where your code is bounded by memory because it requires more bytes and flops, and there are actually a lot of examples for that. But what about Scratchpad memory, or as what all the talk is mostly speaking about NVIDIA GPUs, but yet, of course, you can draw parallel on AMD GPUs. And the reason we focus much on AMD GPUs is that you have continuity on generations all the way from Tesla up till now, so you can start to see trends. Unlike GPUs from other, maybe like AMD or Intel, we don't have such continuity. But I guess the same can apply if you look at newer generations of AMD GPUs. Anyway, so what about Scratchpad memory, or as NVIDIA calls it, shared memory? As you can look here, like on the top, essentially on the figure at your top right, I guess, Scratchpad memory and bytes to flops is just dropping. But what about the figure below on the right? This is the most important figure. This is essentially looking at the scratch padding capacity in megabytes, again, as you go through generations. And you can see that you got a size of Scratchpad memory of increase about 41x over a decade. Yet in the same amount of time, you got increase in flops. Maybe it's not plotted here, but about 25x. So what this says is the capacity of the shared memory or Scratchpad memory is increasing at a much faster pace than what you would be getting from computer pure flops. What does that mean, though? Well, it means we have essentially a huge cache, fairly, huge, in comparison to, like, let's say 12 or 13 years ago on GPUs. As we see announcements from CPU vendors, well, we have seen that already in AMD CPUs, which is what they call vertical cache, which is 3-stack cache. We're getting in more and more high capacity cache on CPUs. It's not clear if this will follow through also to GPUs, but we're sure about, at least in the last 12 or 13 years or so, we have seen such increase in the capacity. A lot of codes were written, or a lot of the fundamentals of programming GPUs were developed over like 12 or 13 years ago on the assumption that you have a limited amount of shared memory or Scratchpad memory, and then they can be very conservative in how they use it, right? So the question becomes, can we use this fact that the cache is fairly increasing in size to be more aggressive in the way they optimize? And how should we leverage this increase in cache capacity? And this is plotting down below a case study we looked at, which is stencils. And stencil kernels, I will explain in the next few slides, but probably the audience would imagine, are neighborhood access patterns that are notoriously and memory bound, not just in GPUs and most CPUs, if not all CPUs. So there are very excellent cases to show what happens when you have memory bound code and how you optimize them. And looking at the accumulated Scratchpad use, if you look at the row on the bottom there, and these are state-of-the-art temporal blocking and spatial blocking libraries for stencils that are used in production. And we're plotting for A100 essentially. How much of this cache are they using? And they're not using much actually. You would imagine that codes like these, which should optimize for data locality, would be using much more Scratchpad. But on average, if you look at this orange line, that's like 25% only of the cache. That's because most of these codes have been optimized, or these libraries were introduced and then optimized over the last 10 years with the assumption that shared memory is pretty scarce. So you should be not so aggressive when you use it. And I'll explain what I mean by aggressive here in the next few slides. Anyway, it's a talk-away message that GPUs are transforming in many ways. I'll explain some of them also in the next few slides, but one main way we're speaking about here is how much of cache memory or Scratchpad memory you have per compute, and there's much of it not used. So also one thing, or one more important feature as I proceed in this presentation, to note that we're having now what they call in NVIDIA terminology grid level synchronization, which is device-wide barrier that has some support in hardware. You have to remember that when GPUs started being used in high-performance computing, I come from a high-performance computing background myself, kernel launch overhead was very high. So people introduced at the time, 2010 or 2008, software device-wide barriers that allows you to try to hide a little bit of that kernel launch overhead. As time progressed, this kernel launch overhead time dropped, but still there is some merit or some quality or some, let's say, there's some motivation in having a device-wide barrier, if not for performance, but also for programmability. And since 2016, we had, at least in NVIDIA, and I think AMD is following up on that, didn't have in the earlier versions of MI, I guess 100 and 100, I think in 300 you will have, which is device-wide barrier, which is essentially a barrier that you can invoke that, across the entire device, all cores or all SMs, streaming multiprocessors. And what we've found, in addition to the previous slide, and where we found that a lot of these stencil codes do not utilize or do not use this Scratchpad memory as they should be doing, what we're looking at also, this actually barrier is improving over time. As we moved from Volta and Ampere, and we have now early testing also with Hopper, this overhead is not so high actually. So we encourage people to use it more. So if you look at, for example, at launching for different, this is like threads to thread blocks, these launch kernel being launched there. Of course, it depends on what you do in the kernel and the parameters and so on. So this is synthetic benchmarks. But here we're plotting essentially the bars themselves would be the grid synchronization, or essentially the amount of time you spend every time you invoke a device-wide barrier, versus this line you see on top there, which is the overhead of the launch, how much time it takes to launch a kernel, which also is a function a little bit of the kernel itself, its parameters, etc. But I think you get the image here that actually device-wide barriers are starting to, I wouldn't say mature, but they're starting to get better and better. So they should be used somehow. So having these two facts of we have plenty of Scratchpad memory and we have device-wide barriers that are quite not so penalizing to performance. How can we use that? Again, we took a use case of stencils. I think I don't need to explain much, but in high-performance computing, from which I come from, stencils are very important because they're used in a lot of PDEs, or partial differential equations. So a lot of applications like in climate, weather, seismic, CFDs, etc. They rely a lot on stencils, and there can be systems. And this is in a study in CGO a few years ago that showed that there are in systems where like half or 2/3 of the cycles of an entire supercomputer just go into stencils. So it's very important to optimize these pieces of simple yet elusive to optimize patterns. Stencils come in different shapes and forms and orders. But you can think of it as you see in the figure on the right, that essentially you're updating each point from the neighbor values. There's a lot of types of stencils. There's also in-place stencils where you're reading from the input and writing in the same place, which is used in implicit methods, numerical methods. But the bread and butter of stencils is not compute in place. It's explicit methods where you read from one buffer and you write to the other. And again, each point is updated by the neighbors. So that probably makes it memory bound, at least not so high order stencils. There are two ways where you would try to increase or improve the locality for stencils. One is spatial blocking, in which you're spatially trying or tile or block your domain such that you get better hits in the cache. And this is, of course, not just limited to GPs. You see that a lot in CPs. And there's what's called temporal blocking. Temporal blocking, as the figure on the right is trying to show your domain as in spatially, and then the y-axis is temporally. You try to mix or merge some of the time steps, because stencils are usually used in an iterative way, in which you do it iteratively over time. And this is what makes it, for example, different from convolutions, which is the same compute pattern, but a convolution is done with a filter once on some domain, while a stencil is usually iterative. So you do it on different time steps and keep on repeating till some algorithm converges. So in a temporal blocking scheme, what you would do is that you take some of these steps and you try to merge them. And obviously here you might have dependencies on the left, on the right, or if it's 3D on the all sides you would have. So you resolve them by one of two ways that I will not go into detail because of the lack of time. One in which you introduce redundancy. You have redundant compute, but then you resolve the dependency on your temporal, just the dimension you're temporally trying to block, or you actually have some form of geometric shape, usually complex, in the way you tile your domain, which you don't need redundancy, but then it's much harder to parallelize. So what we looked at in this case, okay, can we use the two facts we have seen previously, which is you have abundance, fairly abundant amount of shared memory available, and also you have device-wide barriers that helps you to resolve any dependency on the temporal dimension you're blocking. And what we're looking at, okay, this is a simple 2D 5-point stencils, in which the basic kernel is that usually you launch them for each iteration, you launch a kernel once. So you launch a kernel, tell it, I have an input, and update each point by its neighboring points, finish and come back to me, give control back to the CPU. And then you launch again and launch again. So number of kernel launches is equivalent to the number of time steps you're taking in your algorithm. I can basically skip that. That looks more into details how you resolve what they call the halo regions, or the regions where you have to overlap with your neighbors. So what we are showing here is if you have a lot of Scratchpad memory, which allows you to cache the results, so the output from each time step can be used as input to the next time step. Okay, and also if you have device-wide barriers, you don't need to give control back to the CPU. You can sustain what they call a persistent kernel. So you have a kernel that persists, and then while you're persisting in that kernel, you can advance your time steps. How aggressive can you go? Plus, there's a third fact that I haven't probably shown on this slides, which is GPUs now do not need as much concurrency in your code as it used to be 12, 13 years ago. In 2010, there was a paper by Volkov, which the title was nice. It was called High Performance Low Occupancy, which showed that if you write your code in a specific way, include like a lot of instruction liver parallelism in your threads, you don't need as much threads to have high occupancy. This is more so, well, we're 13 years ahead now, because if you look at the latency, and I guess I should have had these figures. Sorry, I didn't have them. If you look at the latency across all operations, be it memory access operations or arithmetic operations, they are dropped significantly since GPUs were introduced. I think the biggest drop was in Volta, right? So the notion that you need a lot of warps to launch on a GPU, and GPU is a throughput optimized architecture, so to high latency, it relied on swapping around warps to hide the latency. You don't need as much nowadays as you would need it before, because nowadays, again, the latency of all operations have dropped. So maybe a small amount of warps is enough to hide latency. And a simple example of, say, stream benchmark would show you that probably on a Volta and also Ampere, you need around 12.5% occupancy to get to peak performance you would get in a stream benchmark. So you don't need as much threads, which also releases more resources that you would have. So if you don't need as much concurrency in your code, right? You don't need to have a lot of work so that the GPU can, move things around to hide the latency. And you have a lot of cache where you can do aggressive temporal blocking, combine a lot of steps together. And you also have device-wide barriers that doesn't cost much for you. It's not so penalizing. Then can we, for example, do what's in this paper, which is we took a domain on the top. And typically when you take a stencil domain on tile, be it temporal blocking or spatial or combined 2.5D or so, you would have different tiles, and then you divide your tiles on thread blocks. So they run in parallel. What we're seeing here is quite different. We're saying just make one big tile and process these tiles one after the other. So you serialize your tiles. And you would say, but is one tile enough to saturate the device? Yes, because as we mentioned earlier, you don't need as much occupancy nowadays. So the question becomes, instead of as you would traditionally take a domain, tile it, and then launch your tiles, this is where you get your parallelism. We'd say, no, make a very big tile. Now you can afford, because you'll only have one tile, like occupying all the cores or all SMs on the GPU. And then because it's running alone, it has all this shared memory for itself that it can use to store the intermediate results of your time steps. It means you can afford to do very deep temporal blocking. And because you have the device-wide synchronization, you don't need to give control back to the CPU for the implicit barrier you usually had in the time loop inside the CPU. You can do all the synchronization you need, so you move the loop from CPU to GPU. And this is essentially what this paper is proposing. There might be other algorithms, of course. I mean, stencil is just one of them, but there's a lot of iterative memory-bound kernels out there that might make use of this way to optimize for GPUs. And as we can see, this is an evaluation in A100. Currently, the maximum Scratchpad memory you get is a little more than 17 megabytes. But you can also use register for additional space. In the previous talk, we heard a proposal, and there's a lot of them, to use register as cache, but this is as you change the architecture itself, so it becomes transparent. But what we mean by using register for additional space, so we treat register as a cache resource in which we can just stash away our intermediate results to read them later. And this can expand because, again, you're running only one tile at a time, so you don't have so much register pressure. So you have a lot of free registers you can use to yourself. So that means you can cache up to 40 megabytes at each time step, which is a lot, and allows you, if you carefully tune your program, to store all your intermediate results. And that allowed us, if you look at the right side, those were methods where you would, or libraries for temporal blocking, very well tuned. And you can see the number in parentheses is the number of time steps. And because they were not aggressive on using this shared memory, so you would see like the number of time steps is 4 or 3, at most 10 or 12 maybe. But using this very aggressive scheme where you have only one tile, which allows you to consume all the resources to yourself, then you can have plenty of redundant computation in your tile, and you can have like up to 40 steps, which allows you, if you plot on the y-axis, here's the performance, like gigacells updated per second, to outperform. Those are, again, very well optimized libraries used in production. With that, I would just say that what we looked at in this research is to investigate 3 things: the abundance of Scratchpad, proportionally to how much your compute can do, and also you don't need a lot of concurrency as you used to, so you can run away with a little bit concurrency in your code, but opens a lot of resources for you. And you have device-wide barriers, and we combined all of these together to have a fresh perspective of how would you optimize memory-bound kernels on GPUs. And this is just extra stuff that we even looked into more stencils, not just the one I showed, one benchmark, even for higher order stencils, like to the 25 point, which means you have more neighbors. And usually that one is more pressured by registers because you need to store the register. You need registers to store the coefficients of all of these points. Even in this case, we were outperforming. With that, I finished and open for questions.
So I know your case study is really great on Scratchpad, so how much do you think it can be generalized to other workloads?
Yeah, good question. Yeah, in this paper, we just showcased the stencil because again, it was a short paper in the workshop. We have expanded that work after submit, even before this submission, which includes a lot of use cases like conjugate gradients, convolutions, and basically anything that's memory bound. In this case, can work, and even compute bound, because even if you have iterative methods where your steps are compute bound, but in between time steps, you have to go to the global memory to store your intermediate result and come back. This is a portion you want to remove. So you would want also to optimize that away, even if your kernel is compute bound. So we did, yes, indeed, look at more compute bound methods. So far, our experience that if it's a steady state iterative method, by steady state means that your compute pattern does not vary from iteration to iteration. This method has been effective. But again, here we just demonstrated a showcase of stencils.
You are mainly a software developer, right? So you develop code to adapt to the new hardware. But you propose a new performance paradigm that is different from what a computer outside will assume.
Yes.
So if you have made some wish list for computer outside and for like I want the GPUs to be changed in this way, what would be?
That's an excellent question. So when I showed this to people in NVIDIA, and I also cited to them that in their programming guide, in the first page, they say, which hasn't changed in 15 years, 13 years since CUDA came out, which advises you to launch so many, threads to hide latency. I noted that this is not true anymore. Showed them even with a simple stream benchmark for memory bound and some GEM like matrix multiplication for the extreme compute and memory bound cases that you don't need that concurrency. They're like, yeah, that's true, but this is maybe not known. Even NVIDIA engineers know themselves, because if you would go and take say cuDNN library or any of the NVIDIA libraries or cuBLAS, and we did something interesting. We ran them on the profiler, which gives you like the launch dimensions, like how many threads and thread blocks were launched. If you did that across different generations coming from Fermi till now, and you vary also the compiler, because compilers also improve over time, you realize that they used to launch like kernels with 192 or 256 threads per thread block. Nowadays, in most of the kernels, if you go into cuDNN, are like launched on 64 threads or so, or sometimes even 32, which is essentially one warp. So they do acknowledge this fact. So they asked me this exact question, and my answer was, number one, like what the wish list would look like is more of this Scratchpad memory, and also more of ways to allow it to exploit the reality that I don't need as much code nowadays to use the device. So let me use it in a more efficient way and expose to me this Scratchpad memory and registers as a resource where I can just think of a library where just define your arrays and just push it there and pull it back as if it's a cache. One point plus, of course, a much more robust and rich semantics for device-wide synchronization. I know they announced in Hopper that there will be what groups, I forgot the name they call, which you can have SMs together, combined in groups, I think TSG or TGC, I forgot the name. And this allows you also to synchronize across different cores or SMs, which means you can map the hierarchy of your program inside it. So I think this is a step in the right direction, and we can build upon that. I hope I answered your question.
Yeah, great. Thank you so much. Yeah.